any accident, whether it's your first or your eighth, in theory, diminishes the value, but I suppose if you get to that high numbers, it's probably not a big deal.
I think mine was on the number 5.
Probably not a big deal.
None of them were my fault.
Okay.
2 of them were pouring out of the car.
Were people just hitting you on purpose?
Well, 2 instances, I wasn't even in my car.
That question still applies. Yeah. You have to be careful, Dave. People might be out to get you. Alright, so, last time we talked about Doppler shifting. Now, Doppler shifting, back, not even that long ago, back about 50 years ago, we started with this concept that the universe is expanding. This was huge in physics. You guys have probably all heard that by now. Everyone's heard that. Doppler shifting was one of the first and largest and most convincing reasons that we saw this happening. Oh, crap. I even forgot the spectrum I printed out.
So I just cancel class.
What?
Cancel class.
Stop it. Okay. So what ends up happening is we get light that comes from distant stars. So let's say it's even white light. And when it gets to us, okay, pretend I'm drawing the negative. If it was white light in the visible spectrum, and we actually put it through a spectrum. Where are you drawing? A spectrum. Oh, spectrum. So if I drew a spectrum here on the board, and it was white light, and what would it look like? White? No, well, no, exactly, it wouldn't. White light separates into all the colors. It would look like a nice pretty rainbow all the way across. Yeah. Now, so if we just looked at a white light source and looked at the spectrum, bang. Now, if we look at a white light source that is coming from the moon and we look at the spectrum, what happens?
It looks like
shifts slightly to...
There's no shifting, not from the moon, not any appreciable number. What happens when light passes through the atmosphere?
It changes color. It gets split.
Well, it's like how the sun, when it's at noon, it's yellow, and then when it's setting, it's orangish red.
Right, and that's a Doppler shift. But more importantly, I'm not really explaining this too well. That's coming from the different angles. What ends up happening is the atmosphere absorbs certain wavelengths. So what you'll end up having is you'll have like these bands that are just pure black. Even though you have white light coming, the atmosphere is going to absorb certain wavelengths of the light, and it's not going to get through. So you have this rainbow with black parts, chunks that were sucked out. Now, what do you got?
And that's why the sky is blue.
No, that's... Yeah, don't you remember that in 2012? The sky is blue, that's because of scattering, light scattering, all the other wavelengths are absorbed. And I guess you could say, yes, that is true why the sky is blue. But let's say that we took a...
It's okay, we can just drop the topic. I was just...
No, you're fine. It's, I should be able to answer these questions more quickly. So the atmosphere absorbs certain wavelengths, and our spectra is going to look like this when we spread it out. Even if we took a spectra through the sky, the blue is the most dominant. There are other colors there. If we put the sky through a spectra, we'll still see a rainbow. Just blue is the most dominant. Okay, but there are certain wavelengths, like individual wavelengths, that are absorbed by particles in the sky that we're not even going to see. All right. Point being is that if we looked at a distant galaxy that is also emitting white light, okay, we're going to see the lines that look like this instead. That is interesting. That is. Why? This is Doppler shifting. What direction is this Doppler shifting?
Left, red, and right's going more towards ultraviolet.
Well, that's what I'm getting to. If we said that due to this Doppler shifting, we found out that the universe was expanding, what direction do we have to be shifted? There's 2 different ways to be shifted: red shifted and blue shifted. And how do you know? Let's say that the wavelength looks like this. This is the wavelength of light that we're seeing. Now instead we have 2 choices. We're either seeing this or we're seeing this.
It's wider.
Yeah, blue shift.
Okay, so we'll vote. What did you say?
What's the bottom?
Why the bottom one?
And it's moving away, then
It's spreading out. So Jared's voting that it's the bottom one. Now Drew's saying it's the blue shift, which is the bottom one. Which is the bottom one.
I voted bottom.
What?
I voted bottom, right?
Okay. One of you is right.
One of us is right?
Yeah. Not everybody. Now, what is the wavelength? What is the visible spectrum of wavelengths?
We all picked the
They'll
bottom.
pick the bottom.
Yeah,
How is one of them
confused.
right?
Well, in that case, Drew's not right. Because he said it's blue shifted.
It's red. It's red.
It's not.
Right?
It's actually, this is known as red shifted. What's the wavelength physical spectrum, Bob? What can you see?
400 is red.
No.
Oh.
That's where we're going wrong. 400 nanometers is blue. 700 nanometers is red. So it goes the other way around. So it goes always blue from the left and all the way up to red. And higher wavelengths until you get your infrared, etc. Okay. Down here you get to your ultraviolet light and there are no wavelengths. Which you're probably thinking of as frequency, the inverse thereof. So, what we're going to end up with is longer wavelengths because things moving away from us. So we're seeing that these spectra, when we're viewing it, and say that this is a nearby star, okay, like that, and then they would see that, okay, the farthest away galaxies, they would then observe, and they would see that they're even farther away, because they're moving away even faster. So just by looking at these spectra of things that are known, that are identical to here on Earth, the spacing is identical between these. And like, why is it all shifted? It's because it's moving away. It's redshifted. So that's how we learn that the universe is expanding.
Well, I thought it's like light from other galaxies are finally reaching us, and that's why we're seeing farther out.
Say that again.
Like how light travels, like it's taken that minute, that's how long.
It takes light a long time to get here. That is true.
So that's like we're seeing more because more of it's get here as time passes.
What do you mean by more of it's getting?
I mean, well, the new is getting here.
That is true.
Not here before.
Well, basically what's happening is we are looking back in time, because the light we're seeing takes so long to get here, we're seeing stuff that's back in time. So by the time the light gets here, you know, it's been 1 billion years or something like that. I mean, really large numbers. So, I mean, for all we know, nothing's out there. It's all exploded. We just haven't figured that out yet. That's going to be a fun morning. But I'm not sure what you mean by that, what you're trying to say.
It's like how I think it's a sphere, it's every light year it's expanding another radius out, and that's how far we can see. Does anybody get what I'm saying?
I do.
Good. Okay. So help me because I'm the idiot who can't understand it.
I think it's saying like a high percentage.
Is there space that we cannot visibly see because the light has not had enough time to get to us, but it's still there even though we cannot observe it?
Gotcha. Okay. So now that makes sense if we want to treat the universe based on the idea of a light bulb, and all of a sudden we can say that, bam, the light went on, and then we're waiting for the light to get to certain edges of the universe to get to us. The problem is, the idea being is after the Big Bang, light has always been at these different places. You have a star that is, by definition, light. So there's no before. Does that make any sense? So to say that we can't see it would actually imply that it was expanding faster than light can travel. Does that make sense then?
I get that. I don't think that's not possible for that to happen.
No, it's not. So that's not possible. In other words, there's nothing out there that we can't see yet because the light hasn't got to us, because that means that it had to, from the Big Bang, it would have had to move farther away faster than the light from it was going here. So, and obviously the light's going to move faster than it is moving away. So, does that help?
Could it technically expand faster when we don't really understand the physics for sure, right?
No, I mean, this special relativity is actually really solid physics. Once we get to the quantum, that's going to be a little bit more questionable. But special relativity is really pretty solid. We have no reason to disbelieve it. In the order of things that physics feels really confident in, number one is electrodynamics. That stuff is solid, rock solid. And nobody's ever been able to prove anything against Maxwell's equations. And number two is probably special relativity. And the reason being is that special relativity jives really well with all of Newton's equations. It works with it, okay? It's the expanded version of Newton's equations, the more complete form thereof. And then everything after that is kind of a big question mark. When you get to the Schrodinger equation, which really does work, and we're going to see that in quantum mechanics, we don't really understand it all that well, but it seems to work. At least these first two we understand work. Newtonian physics is just a lie. We've already proven that it just only works for big, heavy, slow things. And then so you got the different versions underneath that. Things like even gravity, the simplest cases, we don't understand that all that well. I mean, Higgs boson is helping. That's, you know, kind of leaning us towards one direction, but that's just one step in a long path of stuff we don't get yet. Onward. Okay, yeah. All right, so I feel like there's something else that I was going to mention about that, but I don't remember now. Yeah, what do you got there?
So space is expanding.
Yeah.
But when it expands, new things are not necessarily like
Forming.
formed. It's just
Ah.
the empty space between everything gets farther apart.
No, that is not necessarily the case,
Okay.
because you can have stars that are born and stars that explode and things like that. So, in that sense, okay, so if that's the case, then yes, you can have something that has, say we've got a nebula, okay, something that is exploding, and then due to that explosion, we're going to have the creation of another small star or something like that. That star may have already been created, and yes, we have not seen it yet because the light has not happened, or has not gotten here. So in that case, that would be true. That is definitely possible.
But technically, a different kind of question. That's not due to the expansion itself. Or
No, that's under the
Okay,
expansion.
So
It's
when we're
just
expanding, we're just kind of,
the brew pot of mixing of whatever the hell's going on up there.
yeah, it's just like, you add another wing to like a room. It's a bigger room, and until something is put there, it's just empty space.
Yeah. Okay. And then we get to the concepts of what is the edge of the universe, and then I have no answers for you. I run out of things to say.
Well, there's a restaurant.
Which I haven't read that. I really want to.
Oh, it's a good book.
I'm actually partway through. I never read Hitchhiker's Guide,
Really?
so I've just gotten partway through it, and then I started reading dog books on how to train your dog, so I kind of got sidetracked from that and haven't got back to it. So hopefully I will soon. Okay, so what we're going to talk about today, a few things. First one is velocity transformations. Velocity transformations. Okay, last time we did position transformations, and we talked about where things are in position and where they are in time. Now, we need to talk about velocity as well. And it's not terribly more difficult than just looking at position in time, but it is a slight nuance. So we would say the normal transformation equations in non-relativistic space is that u prime is equal to u minus v. All right, so I say that I throw a baseball inside the car as I'm moving, and I want to know what that velocity is in that frame of reference. I need to know within the frame of reference minus the velocity of the car. Okay, the car has to be going that direction. That's how fast the baseball is really thrown. All right, so not going to work for us. So what we need to do is we need to come up with a new definition. Now, if I was to write, what is the fundamental definition of velocity in terms of calculus? Same equation we always use, but on a calculus version.
It's the integral of acceleration or something.
Actually, that's a good point. It is the integral of the acceleration.
That makes sense how you want
But
it.
no, I want the other one.
You want to say derivative of
Yeah, the derivative of what?
like
Time.
distance? Distance and time?
Combine those.
Distance and time?
Yes.
Speed?
So what do I write here?
X over delta t, dt.
Yes, but what's in the top? I can't. This is
X.
there. You go. Dx.
So we're not gonna
It's the time derivative of the position. I'm going to teach you guys to speak like physicists here. Time derivative of the position. Dx dt. Okay. So, and a lot of times whenever we're using that same little equation, Vx, we can always say change in x over change in t. It's just the same concept. That's all a derivative is. So, okay, so we can still do this. This is still valid. The problem is, what is x and what is t equal to? Well, now we have these new systems where we can say that, oh, I'm sorry, this has to be dx prime now and dt prime because we're in the u prime coordinate system. So dx prime and dt prime. Now we just need to know what is x prime and what is t prime. Okay, so we already came up with these equations. We've got our gamma v, there's x minus vt here, and over this one, we've got gamma v minus v over c squared plus t. Those are our transformation equations. Perfect. So now, if we want to talk about the derivative, we will rotate the camera. We'll rotate the camera.
Why doesn't he see?
He's sick today. I actually need to go. He ate raw chicken yesterday because he didn't have the lights on in the kitchen and cut into it and he thought it was white, turned out not to be white, and now he's sick. You did that?
You say raw chicken?
Yeah. He cooked it through, or at least he thought he did, and then he found out that he did later on.
Can you turn the light through and all
And I don't know if you guys have eaten with this guy, but when he eats something, because he runs or whatever, he eats all of it. So like on Tuesdays, we go to a fishbowl all the time when we get wings, and everyone gets 6, 8 wings. He orders 20 every time, and just piles them down. So I'm guessing he probably ate a whole raw chicken. Anyway, all right. So this is going to be gamma v times dx minus v dt. So if we're going to take the derivative of this, we have to take the derivative of both x and t. Now, here's a question for you. Down here, I want to take the derivative of t prime, dx dt. Now, why did I have to put this as dx? What would this have been? A little review of calculus here. You can tune out for a minute. This doesn't affect what we're doing anyways. What's the difference between this one, and this one? What is this equal to?
Any specific moment?
There's something that I can write here. This is not dx dt. That's, what is this?
There's t in it.
No, see, I've got, down here what I've done is I don't have the dx down here, I just have the dt. And up here I have just the dx and not the dt.
So it's a derivative.
It is a derivative, a
Partial
special kind of derivative. This would be the partial derivative of x with the partial derivative of t.
I'm finally using that Calc 3.
There you go. Now, we will eventually start using partial derivatives when we get there. Now, the only thing you need to know, Kyle, is when you take the partial derivatives, they're really handy when you can use them. A partial derivative says, I just want to know about the change of x. I don't care about anything else, even if it does change with respect to x. So that means just the dx, just the dt. Whenever you take the full derivative of something, you've got to take, if there's a tiny change in x, you need to know the tiny change in anything up here. Now, there's going to be no tiny change in v. V is constant. That's the velocity between the reference frames. Gamma v obviously is the same thing, just a function of v. However, your t will change when you change x. You've gone forward and back. All right, so this is the one we want. Sorry for the aside. But yeah, finally using your Calc 3. Stay away from that. All right, so what do we got for this? Now, these cancel. That's handy. So now I've got dx minus b dt. Now what I'm going to do is a neat little trick here. I'm going to divide everything by dt. Okay. So up top, I'm going to have dx dt minus v. And underneath, I'm going to have, I'm going to rearrange this. So I've got 1 minus v over c squared times dx dt. Everyone see what I did there? So tricky. All right, so what is dx dt?
U.
Just u, right? And that's what we're trying to get to. We want to know u prime in terms of u, so this is really handy. So now we get u minus v over 1 minus v over c squared times u. Ta-da!
And that's the simple.
Now that's the transformation, the velocity transformation equation for u prime. What was your question? Or did I answer it?
That's as far as we're going with that.
So far, yeah, that's as far as we're going. Now the only question is, I want to know what u is. We should be able to instantly write this down. What is u as a function of u prime and t prime going in the direction?
So we just solve for u, right?
Well, no, you can't, and the reason being is that this, if you solve for u, you're going to end up with, actually you can. I totally lied, you can. There's no t prime or anything in these. So you would just solve for it. And in fact, you should just be able to tell me what it is by looking at this. If you hold u here, and you put everything on the other side, what's going to happen with all the negatives?
Oh, and then we'll switch.
Everything's going to become positive. So over here you'll end up with u prime plus v, and 1 plus v over c squared times u prime. It'll just naturally work out. And that's because, again, from the symmetry of the idea of this, you have to say that one reference frame is moving plus v, the other one's moving minus v. So that's
Well, it's always like that, right?
It's always like that, right? Now, remember number 10 that you guys, or E on your last homework, it was a big mess. It wasn't just so easy that you could just solve for one. And the reason in that case is because you still had the t primes and the t stuff in those equations. Fortunately, we don't have that problem in here. They're just built into the u's, and they're already been solved for, so we just handle that. All right, so let's do an example problem now that we have these. I will leave those over here. U prime is equal to. And whoops. Alright. And move the camera back. Close the time. Okay, example 2.7. Okay, example 2.7 says we've got Earth. Bob is on Earth, wondering where his Anna is. And meanwhile, Anna says, I'm getting off this planet. And taking off. Off she goes on her spacecraft. Has passed away from Bob Rivers. Off she goes. Alright, Anna is going to move in this direction with a speed of 0.8 c. Meanwhile, Anna sees an object that is hurling towards Earth. It's going to kill Bob. Anna doesn't mind. It is traveling at 0.6 c in this direction. Now, the question becomes, how fast, from Anna's point of view, is that object moving? Okay. So, when we say this is moving at 0.6 c and 0.8 c, what frame of reference is all this from, necessarily? From Bob's. It's got to be from Bob's point of view. Because from Anna's point of view, what speed is Anna going? 0.8. How do I put that on silence? This could be interesting. I'll let you answer this one. Yellow. Yeah, I've only got a second because I'm just in class right now, but I figured as much. Okay. That's all I need to know. I appreciate that. Thank you. Bye. But you don't get a rental car if you do it this way. So sad. That's all it's gone about. Because they're going to set you up with a rental car. You got to have the extra grand or so. But
You should get a truck too.
You have a motorcycle, don't you?
and I've got a big truck as of yesterday.
I bought a truck yesterday.
Yeah, I bought a Super Duty F350 4x4 V10.
Okay, that's cool. Why?
Super incentive.
Does that have the...
I just wanted a giant truck. So my truck without any extra still from the missing Brewers. It's just a tall truck. It's really intimidating.
It's huge.
It's just a 20-foot long truck.
So we're watching your truck.
diesel?
No, it's the V10. Oh, the 10-cylinder. So, yeah, the diesels are nice, but with the maintenance costs and whatnot, and they don't have quite the pickup as the V10. So,
Well, they just got like 4-cylinder kick out on the highway and you get like 28 miles a gallon or something.
you and then the 350. The difference is I'm getting loaded. I'm getting 8 miles to the gallon.
Yeah.
Unloaded, I'll get 13, maybe 14, and the diesels get 16. So you're not talking much between. That's unloaded.
So isn't there what's going to be a new truck because the active is intimidated?
Well, like from New
No,
Dawson.
This truck is much nicer than mine. Mine's an old truck with 200,000 miles on it. It's just huge.
Oh, okay.
So it's a 2005. It's in great shape. It's in fine. It doesn't have very much rust on it. Anyway, stop distracting me, guys. Okay, back to this. If I get plates for it tomorrow, I'll drive it on campus. I had it on campus yesterday. It's fun. You can hear it from a ways away. Okay, what are we doing? All right, this is all from Bob's point of view. Okay, so we're going to call Bob's point of view S. And we're going to call a point of view for Anna S prime here. So S is a stationary standpoint. S prime is a viewpoint of 0.8 c moving this direction relative to this reference frame. Now there's going to be an important point that we need to establish right now. Reference frame we've always assigned to a person, okay? I said I have my reference frame and Jared has his reference frame. Here's going to be the problem. Here in a little bit we're going to be dealing with momentum. So if Jared and I collide into each other, now all of a sudden our reference frames have completely different velocities because they've gone different directions. That's a problem. So what we need to do is establish separate reference frames from the objects that we're looking at. Now, in this case, we have a reference frame S that's the same as Bob's reference frame, but if Bob was to, also get hit by this object and exploded, we would still reference the S frame that was not here. We look at S and see where the plane was moving. Does that make sense? Same thing for S prime.
So one reference plane is stationary, which is Bob's, and then Anna's is the others.
That is moving, right. But even if they were declined and start bouncing all over, our reference frames don't change. We're still considering the one that's not moving, and this one is still moving at 0.8, even if all hell breaks loose, which it will by the end of the day. Okay, so now the question is, what does Anna see compared to this? Anna is going to be U prime. Anna is going to look at this velocity of this object U prime over here. And we need to know what the U minus V, 1 minus V over C squared U. Okay, so we've got U, the velocity that we're seeing here, 0.6 C minus what it says is the velocity between the objects, 0.8 C. Alright,
So
divided by,
does it not know the direction?
it does. Darn it, you didn't let me get all the way through it. I was going to solve it incorrectly and show you what goes wrong. Okay, here's the problem. We have to set up a positive and a negative direction, and you have to be painfully careful to stick with it. Okay, we're going to sit here and set to the right is the positive direction. V is a positive 0.8 C. Everything that moves to the right is positive, everything that moves to the left is negative. Careful on this. All right, so if that's the case, then we're going to say that U is actually a negative 0.6 C minus 0.8 C. That matters. Now, down here, we're going to have 1 minus our velocity, which is 0.8 C of the reference frame, divided by C squared. And then we're going to just be multiplying by, I believe, U. Yeah, U again, here's the negative 0.6 C. Now, when you're doing these calculations, again, you don't have to worry about the C's. Who cares? All the C's down here are going to cancel. You're going to end up with 1 C left over in the numerator. So you can put this into your calculator as, I'm going to have, negative 1.4 divided by the quantity 1.
This is supposed to be multiplied on top, right? Not
Yes, sorry. I'll draw it like that. 1 minus whatever that quantity is. So you can put this into your calculator as 0.8 times a negative 0.6. This is all you have to put into your calculator, and you're going to get an answer of what? Some calculator. Push the buttons. Bring your guys' calculators. Practice. You get the same thing?
Yeah.
0.946, I believe.
Yeah. Negative.
Negative 0.946 C. Alright. Good. Now, what does this mean? That means that the second object here, between from Anna's point of view, this object is flying at her, she's just staying stationary, at almost 95% the speed of light. Now, this is a high number, but it's not exactly particularly surprising. From Bob's point of view, what does Bob see? Bob sees them coming towards each other at what velocity?
Oh. 20.6?
No, but in total, how fast is, from where he sees Anna and where he sees this, he sees them approaching each other. At what rate is this gap closing?
1.4.
1.4 C. He sees this gap closing at 1.4 C. Now, here's an interesting problem I'll tell you guys that I put on the calculus physics test yesterday that a couple people didn't like. It's all about relativity. I say that Anna and Bob, I don't remember the names, but why not? Anna and Bob are in this class, so.
You meant you were throwing up other people questioning how Bob Ross was?
No, I haven't done that since 2212, but that was good times. We had lots of Bob Ross. No, Anna and Bob are 100 meters apart from each other. Anna is moving towards Bob at 2 meters per second. Bob is moving towards Anna at 3 meters per second. Bob has a dog named Dog. Dog runs at 5 meters per second. So, if you have this, you have Bob running this way, Anna running this way, and you've got Dog running between them. The question is, how far does the dog run in total if it just runs back and forth between them? So the dog's going to go like this until they meet. if you were to integrate all of this distance, what would that be? Now this seems like a pain in the ass to figure out, okay, so the dog gets here, how far has Anna moved, etc. You don't have to do that. You have to simply think about it in terms of time. This is a very simple problem. They are moving.
Dampening, is it?
What?
The dampening.
That's what it looks like.
Yeah.
In fact, if you were to plot it, it would like that, like if you were to add it. But as far as the numbers go, if we've got 3 meters per second and 2 meters per second, what rate is this gap being closed at?
5 meters.
5 meters per second.
So just
In total, they have 100 meters to cross between the two of them, right? And they're closing the gap at 5 meters per second. So how many seconds is that going to be until they close? 20. If the dog is running at a constant 5 meters per second, I don't care what direction it does, it's going to run for 5 times 20, 100 meters. So you can add the different steps up. It takes 20 minutes to do it. In fact, what ends up happening is you'll find out that the first step is about 70. The next step is about 17. The step after that is 7. So here you're at about 96 or so. Right? It's 94. And you keep doing, and the next step is going to be 2. And you're obviously going to get tinier and tinier steps because right at the end, it's as if the dog's going back and forth for fractions of a second. You slowly are getting up to that.
So, what's the right answer?
What?
What's the right answer?
Actually, I had the highest grade I've ever had in the class on this first test. A whole quarter of the class got 100% on the multiple choice.
How many?
About a quarter of the class got
Yeah.
a perfect score on the multiple choice.
That's-
This is one of them, so.
That's the average.
This is a multiple choice question?
Well, it took 5 seconds to figure out. I just showed you how to do it. But, so, they got it. All right. Back to this guy. All right, Bob, 1.4c. Is this okay? Are we okay with this? Nothing can move faster than c. We said this. So why are we okay with Bob going 1.4c? They're seeing this as this gap closing at 1.4c?
Well, just cause something's close. Nothing's moving at that speed.
Exactly, and that's the trick. There's nothing wrong with this 1.4c. This is perfectly fine. What you can't see, no observer can see any object moving faster than the speed of light relative to themselves, relative to their own reference frame. He's not saying either one of these objects individually is moving 0.9c. He's saying that he's trying to say that the closing of the gap between them is larger than that. Whatever, fine.
That's moving away at 0.8 and it's moving forward at 0.6.
Good. Well, you guys grabbed onto that right away. That was confusing to the last class. Okay, onward. All right. Yeah, next part. Now, before, what about position in the y and z direction? Remember we were dealing with that? What was the equation that I had for y prime in terms of y and z prime in terms of z?
It's a constant.
They were constant because there's no motion in that direction. So that's really handy, y and z. All right, so now if I want to know u prime in the y direction, I can write this as dz, or no, dy prime over dt prime. And am I going to get just dy dt back, same as I had before? Why or why not?
So you can never have an integer greater than 2, right?
Huh?
Is that pretty slow?
Yeah, I suppose that's true. You can never see anything that's greater than 2c. Because you can never, yeah, that's a good point. You can never see two objects approaching each other faster than 2c. Never thought about that. Is this true or not? Why or why not? Well, first of all, is this true? The change rate of y prime equal to dy. Why?
They call it just doesn't make sense.
Well, it turns out that this part is true. There's nothing wrong with this.
Is it because there's no velocity in that direction?
There's no, it's not moving in that direction at all. Right, there's no velocity in that direction. Since y prime is equal to y, we're fine with that. Z prime equal to z at all times, because we're not moving in that direction, we're fine with that. Problem is, and we've already shown this, that the dt prime is not equal to dt. There is a change in the time component. So, unlike just for position, since we have this dt in here, things do change. Where am I? I'm off. So, dt prime is not equal to dt. Yay. Alright, so what is dt? Well, we did this last time. Remember, we had the same thing from when we were dealing with the x position. So I can say that u prime y is simply going to be equal to dy divided by our gamma v minus b over c squared dx plus dt. So I've got the denominator that is the same as looking at the u prime in the x direction. The numerator is just simply dy. And that part's kind of nice.
What's the dx in there?
Why is dx in there? Because our change in time, the difference between these times, is a function of the x coordinate because that's the direction that we have motion. Time dilation and everything like that happens in the x direction. So to figure that out, we need to know that the rate we're moving. So now I'm going to apply the exact same trick that I had before, divide everything by dt. So I'll get u prime y is equal to dy dt over gamma v minus b over c squared dx dt plus 1. And I can write this as u of y divided by gamma v minus u of x v over c squared plus 1. So to figure out u prime y, we just need to know whatever the velocity in the y direction is of the other object. And then we got this screwy thing down here. The obnoxious part about this is gamma v sticks around. It doesn't cancel. So we do have to figure that out. And obviously for the z component, it's going to be identical. We'll still have the x component at the bottom. Down there. That makes sense? Okay. All right. Now you're supposed to have a homework assignment that practices this, but you don't. Lucky you. Okay.
So we have homework assignment today or not?
Nope. Yeah, homework assignment on Tuesday. It won't be that much longer. I'll probably only put 2 extra problems on there that I was going to assign you there. So I guess in the end it's a net benefit. Because you don't have a full assignment today. So it'll be slightly longer. Alright. Newton's laws. What is Newton's second law? Most famous one. That should have it.
E equals mc squared.
That's not Newton.
The reaction thing is equal off the reaction. That's what we're talking about. Am I good?
Thanks. We will have that equation, though. We will deal with that. Just not yet.
And force equals mass times acceleration.
Yes, F equals M. Okay, so.
More topics to apply.
Mass times acceleration. And for those of you who had me in the intro stuff, I'm a real jerk, and I make sure that you write all the vector symbols, and I make sure you write F net, because again, it only matters the net force. Okay, turns out that this was a wrong equation, or at least an incomplete equation. So we're going to expand this into something a little bit larger. The true form of this equation, this was originally how it was understood, but let's stay with me on this one. F net, what's the calculus way to write the acceleration?
Are we switching the sections?
No, we're just, yeah, we're on section 2.7, I think.
Momentum and energy.
Wait a minute, where are we? Yeah, we moved on to momentum and energy.
It's the integral.
Yes, dv dt. dv dt. Okay, so basically we can say that the F net is the mass times the rate change of the velocity. Now, the interesting thing about this is, what if I was to write this as such? That F net is equal to instead dmv dt. If I bring the mass in there. If you're taking the derivative, the time derivative of something that doesn't change, like mass, what happens? Mass just comes out up front, right? So there's no difference in this. Okay. What is this quantity here? Mass times velocity. Yeah, you're on a roll. 3 in a row. F net is actually equal to the change in momentum as a function of t, dp dt. terribly surprised about this. Does anybody remember the long momentum equation? We say that we've got this impulse, J of x is equal to what? It's equal to an integral of something, here I'll help you out, which is equal to the change in momentum, which is equal to momentum final minus momentum initial, etc. And we can write this as m final, and I used to write this equation out in like 7 different forms, you can write along. What is the integral part of this? Remember when we were talking about impulse? And we had baseballs. You hit a baseball with a bat, and it was in contact for a certain amount of time with a certain amount of force.
Acceleration in there?
No. Yeah. Yes, not over though. Force times time. So this is force times time, or whenever we had a constant force, we can do F average times delta T. So we actually dealt with this equation before, we just didn't talk about it. Now, if F average times delta T is equal to delta P, then I can say that F average is equal to the change in P over the change in T, which in calculus terms is this, the derivative of the momentum with respect to time. Now this matters because in some cases you can have a change rate in mass. Let's talk about spacecraft for a second. You might be moving at have a constant exit velocity of your fuel, but you're having less and less fuel. So in this case, your change in force is due to the change rate in mass that you're expelling out of the back of your spacecraft. Now it's not the most common example that we work with, but it does work.
What are you taking from that? What are you doing with that?
This whole thing. I'm saying this whole thing is equal to that whole quantity over there.
These two things are the same. Oh,
Now it has arrow and bubbles.
you're kind of off the board.
Gotcha. Okay. Well, I'm going to erase all this in a second. So we'll get back over here. Alright.
Yeah.
So you now know a new version of Newton's second law, which we're going to take as the more correct version. F net is equal to the change rate of momentum with respect to time. Alright, what are we going to do with that? Well, we're going to move on to talk about these equations. Now, we say that momentum and energy. Anytime I say the word momentum, I think of that Bill Nye video. Man,
Let's
all
watch
the
it.
stuff that was missed. You're the only one who knows all these things that I'm referencing. Momentum one. The motorcyclists that were playing the kickball game.
You should watch it so that you can
should
watch
watch.
it. Put them on Blackboard and watch it.
There we go. I'll put the link. I can probably do that.
Watch them in class.
Momentum and energy are known as two of the blank laws that we studied in 2201 and 2211. What? No. There's a special word in here that allowed us to make equations a whole lot easier, going from potential energy to kinetic energy, and our changes in momentum, because momentum and energy are blank laws.
Yeah, that's okay.
It's the title of the entire section of all those chapters. Think tree hugger. I don't know if that's going to help or not.
Hip laws?
I'm just going to throw out words so we get it.
Okay. Think recycling.
They
Waste management?
the R word. It starts with an R.
No, it does not start with R. Momentum and energy. What?
Let's talk about that.
C.
Oh, no.
Think recycling.
I remember talking about this at the end of conversion. I'm going to use that at the end of 22 or 11, right?
Why can we say that a ball that is dropped up here has a certain amount of potential energy, and we can directly calculate? There you go.
Oh,
Conservation law.
duh.
Think recycling. I don't know what keywords was going to happen. Man, picking up code speak. Okay. So, to do this, let's do the standard way first. All right. Momentum and energy are conservation laws. This is important because they're going to be conservation laws in all reference frames, whether we're in special relativity or Newtonian mechanics. If this is going to be true, we need to find a way to make it true in everything. So, on to the next subject. How do we make this possible with special relativity? First, we've got P total. Okay, we're going to talk about our total momentum here in P prime. So, in other words, I have some momentum of 2 things, 8 things, 12 things, I don't care, hitting each other in the initial reference frame. Now I want to know what is going on in our new reference frame. So I can say P total is going to be equal to the summation of Mi times our Ui prime. Now, I'm getting back to the Ui, because remember, the V is always kept specifically to be the velocity between the reference frames. Ui, instead, is the velocity of whatever object it is. Now, for this, we're saying the mass of whatever the object is times the velocity that object is going. If we add all of these up, that's our momentum total. And that's how we used to do with the balls colliding. And of course, we had to have the positive direction, the negative direction. We had to make sure we kept all that straight. Still got to do all that. Okay. So, how can I write this? Well, I need my transformation equation for U prime I in terms of the other one. I'm trying to figure out what my momentum total is as a function of momentum in the other reference frame. Wow. Okay. I can now write this as the summation of Mi times what we have is Ui minus V. And this is going to be equal to the summation of I times Mi Ui minus the summation of I Mi V. So I can write this as P total prime is equal to P total minus this quantity MIV. Alright. What did I just prove? What the heck was the point of any of this? Okay, I'm saying that momentum in a difference reference frame. Now, is this, what I just did here, this little magic, is this Newtonian transformation or is this special relativity transformation equations? And how do you know?
I'm going to say special. Okay. Because it has a U, but that's for a really bad reason.
Is that
I'm
first
gonna go
P
the other
total
ones if you
prime?
want just to disagree.
P
They're
total
little-
prime.
Okay.
These are both primes.
I couldn't tell if that was, okay.
The board or not.
Yeah.
Or bad missing on my part. What do you got?
The opposite of what he said.
Oh, it's just to be the opposite of what he said.
No, like, we don't, I don't know.
What I did was here is I said U prime is equal to U minus V. That's Newtonian. Remember, that's how we started the day with, and then we came up with special relativity. So this is still Newtonian. All I'm saying is that if we have a reference frame and we're watching something in Newtonian mechanics, and we've got some certain amount of momentum in there, we're saying it's conserved, then it better be conserved in another system. So, I'm saying here's the momentum in the new system is equal to the momentum of the old system. So if this changes, then this is going to change. But what about this? There's an extra quantity in here. Well, what can you tell me about this extra quantity right here?
It's 0.
Not necessarily 0, but it is constant. It is a single value. Why? Because, again, we're dealing with reference frames that are moving at a constant velocity with respect to each other. So V is a constant, and we're assuming that the mass of all these objects, I mean, maybe they... Oh, thank you. The mass of all these objects is adding up to the same value. Okay, maybe something, got stuck a little bit on the other one, but that means that the total mass still with all the objects that are involved is still the same. Make sense?
Mm-hmm.
Okay, so this is a constant. So in other words, if this changes, goes up or down by 5, 6, whatever, this one has to go up and down by the same 5 or 6. It doesn't change. It can't change. Alright, so that means that if that is true in Newtonian mechanics, we need to make sure that it's going to stay true in relativity. So let's fit. Alright, let's get rid of all this. Oh man, I feel like I'm going to keep seeing my Alright, example 2.8. Alright, 2.8 says we've got an object which will now give mass of 4. 4 what? Who cares? 4. It is moving at 0.6 c. We've got another object of mass 3, 0.8 c. Or whatever kind of units you want to use. Don't matter. Doesn't exactly. So, what is the total momentum of this system? And how do you know? Run the math. Do it.
look like you're fighting with yourself here. Yes. Okay. How do you know it's 0? Well, 4 by 6 is 24, and 8 by 3 is also 24. These are the same values. So in other words, we've got, just like how you shook your head at me. So we've got 2.5. It just is. The math says it is. What do you want me to say to this? No, I understand. All right, so we've got a momentum of 2.4 c going this way, and momentum of 2.4 c going this way. So our total momentum for the system is equal to 0. All right. Without doing any math, we're going to say that these things collide off of each other. I really should have drawn them the other way because it's wider. 4 and 3. What can you tell me about my velocities going in the other direction?
They should be equal and opposite.
Equal and opposite. They necessarily have to be. So we're going to have 0.6 going out this way and 0.8 going this way. Now, why? Because first of all, that still gives us a total momentum change equal to 0, but also because of energy conservation. Okay. And this is an elastic collision. So we could run the whole energy equation to figure out that this is true, but I think we're content knowing that it is. Just by looking at this, you can say that the energy is still the same in the total of the system. And we know that the momentum still adds up to 0. Therefore, if this is a possible answer, this gets into math reasoning. If this is a possible answer to this equation, which it is, because the momentum is 0 and the energy is still the same, then it's the only answer to the system. Does that make any sense?
Yeah.
Blah. Okay. Anyway, now, page 4. From this point of view, now, what reference frame are we taking these velocities relative to? No, set.
Someone's watching.
Right, okay. So we have some sort of reference frame here, S, who's just sitting still watching these happen, but it's not in either of these reference frames. So now let's take an S prime reference frame that is moving with a speed of 0.6 c going this direction. Off we go. Wait a minute, I want to make sure I did that right. Oh, because it doesn't matter. Huh, that's why, of course. Okay, so we've got a reference frame here moving at S prime, going this way at 0.6 c. Now, what is this going to look like from their point of view? Let's do the before.
The 0.6 is moving the 0.8 there. Yes.
Say again?
That the 0.6 is moving the 0.8 is.
I agree.
It's almost like we're traveling.
4 has 0 velocity, and the 3 is going to be moving this direction. Now, what is 3 going to be moving at what velocity? How do you know? Everybody's sniffling right now. What the hell just happened?
I'm not simply.
1.8.
I was this morning.
What? Alright, so what speed are these going through? Without doing calculation, how do you know?
0.8.
No, not 0.8. They're moving at each other at 0.6 and 0.8.
The number was down 4.
Exactly. It's the exact same situation. So we can go back to the problem we just did a minute ago. Remember when Anna's taking off in her spacecraft at 0.8 c, and we said that the rock was moving towards her at 0.6? Now we're moving in the opposite directions, but the answer is still going to be 0.946 c. Does it matter that now our reference frame is only moving at 0.6 c, instead of last time our reference frame was moving at 0.8 c? Why does that not matter?
Could you repeat that?
Okay. In this case, last case, we had a reference frame moving at 0.8 c. And we had Anna going this way at 0.8 c, and we had the object coming this way at 0.6 c. Now it's the opposite. Now our reference frame is moving at 0.6 c, and we have the object moving us at 0.8 c. Does that matter? Why or why not?
No.
Why?
Oh no.
Let's think of it this way. Okay.
So, let's say you and I are the objects that are moving towards each other. Now, you are Anna originally in the spacecraft, and I'm the object that's going to hurl to Drew's death in this case. Drew, you get to be Bob because you're in that direction. Okay, so you're saying that I'm approaching you at 0.946C, right? That's what we calculated before. So now if we take your reference frame and my reference frame, and your reference frame in the previous problem was S prime, it was the same, moving at 0.8C this way. What would you say the velocity between your two reference frames is? It's the same answer, the 0.946C. Because now, from my reference frame, it's the same idea. I'm moving towards you. Well, I see that I'm not moving at all, you're moving towards me. So that velocity, V, that you see between one reference frame and then the way that they see it is always constant. That's one thing that doesn't ever change, remember? So if I say Drew is moving away from me at 5 miles an hour, Drew's going to say the exact opposite, that I'm moving away from him at 5 miles per hour. That has to be constant. So from my point of view as the asteroid, I'm going to look at you moving at me towards me at 0.946C, because that isn't an object within your reference frame, that is you as the reference frame coming at me. And you're referencing me as the object coming towards you. Does this make sense? So, okay, kind of. See, I'll draw, here's Bob. Okay, we had him on S. Now we've got Anna and her spacecraft going that way at S prime at 0.8C. Now we've got this object that is coming back this way at 0.6C, and we'll call this one S double prime. Oh, I just need to know this. So annoying. Alright. S double prime coming this direction. Now, if from her point of view, this object is coming at her at 0.946C, then from his point of view, she has to be doing the exact same, because from his reference frame, he's referencing the object coming this way. So now what we're doing is now we're calling this reference frame S prime, and we're just switching it such that instead of traveling to the left, it's traveling to the right at 0.6C, and an object is coming at it at 0.8C, which is the exact scenario that we had before. So the answer still has to be 0.946C. Okay, I'm hoping we're kind of getting a feel for this stuff. We're not too far away from the test. Okay. No, I don't know when yet. Whenever we get done with the chapter. Okay, so 0.946C. Now, what is our momentum total here? Not 0 this time. Not 0 at all. What would our momentum total be? Roughly.
30.
What?
What was it, 30?
Yeah, because it's going to be 3 times that. So if we multiply 3 times that, we're going to get our total momentum is equal to negative 2.84C. And it has to be negative. It has to be negative because we're pointing in that direction. Now this isn't a big deal, because just like before, we said that we can have different velocities, but they have to be the same. The only thing we need to know is after the collision, if in fact we still have the same momentum, okay? Because we need to have the same momentum before and after. Otherwise, this doesn't work out too well for us. All right, so now we've got here 4. And we're going to say it's going to be going this way, and 3 is going to be going this way. Now, what direction is our S prime moving again? We have to keep this in mind. Our reference frame that we're looking at, this S prime, is still going this direction at 0.6C. That's the velocity between the reference frames. And Bob is still standing over here at S. Oh, I'm dying. I suppose that's an exaggeration. So, from Bob's point of view, we said that the 4 went off in that direction at 0.6C, and the 3 went off in this direction at 0.8C. Now we need to know, from a reference frame that's moving at 0.6C, how these change. Sorry, guys. Oh. Okay, now, we didn't have to run the equations for this first one, but we could have. If we ran the velocity transformation equations that we just saw at the beginning of class, we would have saw that this one is 0 and this one is 0.946C. I'd rather see you guys be able to rationalize that. All right, so I need to move this over now. Okay. All right, so that's the momentum before. Now let's.
question.
Thank you. This is equal to negative 2.84c. Now we need to know afterwards. I just want to write over here. Okay, in order to do that, we need our equation. Okay, it says that u prime is going to be equal to u minus v over 1 minus uv over c squared. Now, fortunately, everything is still in the x direction. There's no y or z. Everything's just going in that direction. So we don't have to worry about any of that other stuff. So, plugging this in, we have to just be painfully careful that we're using all the right numbers here. 0.60, let's do this first for the 4 and figure out what direction the 4 is going. My u, what is my u value for the 4? Drew. Class done 5 minutes, I'm not fast.
Alright, yeah, 3/4. But are we staying up by any more pages?
It's 0.6.
No, not quite.
Oh, wait. This is a question. U is the movement of the object itself and not the reference frame?
Right.
Okay.
V is always the velocity of the reference frame. U is the object of, or is the velocity of the object in the original viewer's reference frame. And it's really hard to look at that. So U is the speed of the object in whose reference frame?
In their reference, our reference frame, and U prime is it's in theirs.
I don't know who you and there are, but sure.
Yeah.
Bob. Bob over here is an S prime steady
So
still.
that's then, okay. Then
And this S prime is the new one, which we can call anything else that we want. So we've got S and S prime. So yes, I want to know, I need to know the velocity of the object in S. What's that going to be?
4, would it be 0.6c?
No, we're doing with the after. We already did the before. Here's the before stuff. Now we're down here. It's okay, I'm going to move this along, so we got to get out of here. It's going to be negative 0.6c. Negative 0.6c. This is the velocity that Bob sees the object moving in his reference frame after the collision. So then we've got the velocity of the difference between our reference systems, which is positive 0.6c. So then underneath here we've got 1 minus negative 0.6c times 0.6c over c squared. All the c's cancel again, so we're going to have 1 minus a plus 0.36. Here we've got 0.6 times 0.6.
Why are you multiplying?
I don't know why I'm doing that at all. Minus, so we're going to get an answer here of negative 1.2c divided by, that's going to be 1.36. So we get an answer of, where did I write it down? Negative 0.0882. 882c. So, negative 0.882c. Now, in the other direction, 3, same equation. Now, for that one, I can say that I'm equal to 3. We say Bob thinks it's moving positive after 0.8c minus 0.6c. And this is going to be 1 minus a positive 0.8c times 0.6c over c squared. So we're going to get an answer of 0.2c over 1 minus what's going to work out to be 0.48, so 0.52. So you can start to do this stuff in your head. You don't even need calculators. The c's always full out, and you're doing 1 minus some little fraction. It really is not too terribly difficult to do. We get an answer here of a positive 0.385c. 0.385c. Okay, so last thing to do is to check the momentum for this. Our total momentum for this is going to be the quantity 4 times a negative 0.882c plus the quantity 3 times 0.385c. And I don't actually have the answer written down here.
Negative 2.38c.
Yeah, negative 2.83c. Negative 2.38c. Okay, that does not equal negative 2.83. foreseen. There's a huge problem with this. Momentum being a conservation law necessarily has to be conserved. I don't care what reference frame you're in, these things have to be true. So what's happened is, even though we use our handy-dandy little velocity equations, it turns out that momentum needs more work to jive with special relativity, such that we get momentum before equaling momentum after. So first thing we're going to do on Tuesday is we're going to solve the Lorentz transformation equations. So special relativity for momentum.
So does this cycle at MA need more work?
Yes. So basically, I don't know if you guys have noticed the pattern, but what we're doing is we keep looking at something in Newtonian, simple position changes, simple time changes. Then today we did velocity, now we're going into momentum and energy. So we keep taking all of these equations that we learned once and relativizing them to invent a word.
No homework.
We'll see so.
Sure. As far as what I'm going to do Tuesday,